Hi and welcome. I'm Meghna and you're watching the Learn Electronics India YouTube channel. In this video, we will be learning about semiconductors and diodes. We will understand the basics of a semiconductor, how it behaves and how it functions, followed by characteristics of diodes. Let us get started with what a semiconductor is. Materials are broadly categorized into three types: conductors, semiconductors, and insulators. This is based on their conducting properties. While conductors have a lot of free electrons and they can easily conduct anything like heat or electricity, insulators do not have much of free electrons. Now, semiconductors is something in between conductors and insulators, which means they can behave as both conductors and insulators by some external factors. So this property of semiconductor is extensively used in designing many electronic components and circuits. This image explains the semiconductor structure. Now every material again has got two different bands. One is the valence band, another one is the conduction band. Valence band has electrons that are bound to the parent atoms. They are tightly bound and they cannot easily move, unlike the electrons in conduction band. So it is these electrons in the conduction band that help in conduction of current or heat. These E minus is known as electrons, that is negatively charged, and these white color holes, they are called as holes, or it is also called as positively charged particles. Basically, because there is an absence of electron, it would have gained positive charge. Now, something called as band gap decides how a material behaves. So, band gap is the energy difference between this valence band and the conduction band. It is also called as energy gap. This band gap is very much high in insulators, but it is almost not present in conductors, and it is much lower than insulators in semiconductors, which means when more electrons from the valence band jump to conduction band and the number of electrons in the conduction band increase, it means the conductivity of that material increases. So upon supplying with external energy to a semiconductor, that can be either in the form of heat or voltage, the electrons from the valence band, that is here, will gain that excess energy and they can clear this band gap and jump to the conduction band. Once these electrons are in the conduction band, they help in conduction, which means in this case, the semiconductor is behaving like conductors. So by applying sufficient amount of electrical energy or heat energy to a semiconductor material will make it behave as a conductor. And in the absence of that external energy, or when that external energy is not sufficient enough for the electrons to jump from valence band to conduction band, then the semiconductor behaves as an insulator. So again, semiconductors are majorly classified into intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductor is which has no impurities. Impurities means it doesn't have atoms of any other element in it. That we call it as intrinsic semiconductor. So it is a pure semiconductors. And the number of charge carriers will be relatively low, basically the valence electrons. Germanium and silicon are considered to be two most important intrinsic semiconductors, and this is how the lattice structure looks like. So it will have 4 valence electrons and it will share that electrons with other atoms of silicon to form a covalent bond. For now, we just have to understand that there is just silicon atoms everywhere. Now, when we add an impurity or when we add an atom of another element, it becomes an extrinsic semiconductors, that is doped with impurities, and it modifies the electrical properties. In this extrinsic semiconductors, the electrical conductivity is more because obviously there are excessive charge carriers present in it. Again, extrinsic semiconductors are further divided into N-type and P-type. Before that, let us understand what doping is. The process of adding impurities intentionally in a semiconductor material is known as doping. So if you can see in this first image, we have added phosphorus, and in another image, we have added boron. So these are extrinsic semiconductors, and the impurity that we add, that is called as a dopant. So in this case, phosphorus is a dopant and boron is also dopant. Depending on the number of free electrons that are present in this dopant, we have N-type semiconductor and P-type semiconductors. When a dopant will add free electrons to a semiconductor, like the case of a phosphorus, then it increases the number of electrons. Electrons means negatively charged, so it becomes a N-type semiconductor where the majority carriers are electrons, for example, phosphorus. Similarly, when we add an impurity that has less number of electrons, that is called as an acceptor dopant. So it will create a hole in the lattice because of absence of electron. There will be a hole and that will create more positive charge carriers. So positive means p-type semiconductor, and in that majority carriers will be holes. Again, boron, for example, is an acceptor dopant. And there is an absence of electron here, so there is a void, so we can consider it to be a hole. Now, all this property of a semiconductor is used in designing a diode. So a diode is a semiconductor device and it allows the flow of current in only one direction and blocks it in opposite direction. So it can be used as a switch. Inside a diode, there will be a junction called as a PN junction because we will use both P-type and an N-type semiconductor material. As discussed earlier, it is mainly used as electrical switches that allows current in only one direction, that is when it is forward biased, and blocks when it is reverse biased. So here you can see a PN junction. In P, positive charges or holes are excessive, and in N, negative charges or the electrons are excessive. Now this will form a junction because we know that opposite charges attract each other. So all the positive holes will come and form a layer here. Similarly, from the N region, electrons will come and form a layer. Now this layer, we call it as the depletion region. So a depletion region is a thin layer at the junction of P N diode where there are no free charge carriers. So this hole has paired up with this electron. Similarly, an entire layer is formed like that and there are no free charge carriers. When we break through this depletion region, there will be flow of current. That happens by the process of biasing. So there are two types of biasing, forward bias and reverse biased. When the positive terminal of the source is connected to the positive terminal of the diode or the anode of the diode. This is nothing but the p-type semiconductor. And when the negative terminal is connected to the n-type semiconductor or the cathode, then we call it as forward biased. So positive should be connected to positive, negative to negative. At that time, we say the diode is forward biased. When it is forward biased, it will reduce the width of the depletion region and allows the current to flow through it. Vice versa is the case in reverse bias. So when I connect the positive terminal of the voltage source to the n-type semiconductor or the cathode and negative terminal I connected to the anode, then it becomes reverse biased. In this case, the width of the depletion region increases, which means the current cannot flow. Hence, biasing of a diode plays a very important role in electronic circuits. This image clearly explains the biasing of diode. This is forward bias and this is reverse biased. So P-type, there are more holes and that is connected to positive terminal of the battery. And N-type, where there are more free electrons, that is connected to negative terminal of the battery. Hence, this is forward bias and you can see the narrow depletion region. Whereas if we come to this image, the N-type or the cathode is connected to positive terminal of the battery and p-type of the anode is connected to negative terminal of the battery. This results in increase of the depletion region followed by no flow of current. So the characteristics of a diode varies when it is forward biased and when it is reverse biased. This graph explains that. So when a diode is forward biased, there will be low resistance and smooth flow of current. As the forward voltage increases, there comes a point where this current increases exponentially and it reaches its peak current. Similarly, in the reverse case also, the reverse current of the diode increases and after some point, breakdown occurs and the reverse current increases exponentially. Now let us understand other characteristics of a diode. Every diode will have its own threshold voltage in practical cases. Ideal diode, there is no threshold voltage, but in real life or in practical cases, a diode has a threshold voltage or a cut-in voltage. That is the minimum amount of voltage that is required for the diode to conduct. So if you can check this graph, it is written 0.7 volt for silicon and 0.3 volt for germanium. This is nothing but the threshold voltage. So suppose I'm supplying a voltage of 1 volts in that and I'm using a silicon diode, 0.7 volts would be consumed by the diode itself to get activated and to conduct current. Dynamic resistance is another characteristic feature of a diode where it increases in the reverse bias region and decreases in the forward bias region. But when the diode reaches breakdown in the reverse biased, then we have seen that the current increases exponentially, the reverse current. This means in this case, the resistance varies. But other than that, in reverse bias, resistance of a diode would be high. Forward voltage drop is the voltage across the diode when it conducts in forward direction. This varies with material and temperature, just like how we studied for silicon and germanium, different voltages. Another important characteristic of a diode is the reverse recovery time. So when a diode switches from forward to reverse bias, there will be some amount of stored charge. And for this charge to get dissipated, the diode consumes some time. This time is called as reverse recovery time. So you can see, if you can see this line, there is slight kink over here or a slight bend. So for a diode to dissipate that amount of energy, it will take some time. So that was about the basics of a semiconductor and the diode. In this video, we have studied how semiconductors can behave both as conductors and insulators, how we can vary the external supply and the importance of doping to alter the properties of a semiconductor material according to our needs. Further on, we have understood how semiconductor is used in making diodes and how a diode behaves when it is forward biased and reverse biased, followed by its characteristics. Visit our website for more information. See you in the next videos. Thank you.